Chapter 21: Electric Charge and Electric Field. We covered these topics in this chapter: static electricity, electric charge and its conservation, electric charge in the atom, insulators and conductors, induced charge, the electroscope, Coulomb's law, the electric field calculations for continuous charge distributions, field lines, electric fields and conductors, motion of a charged particle in an electric field, electric dipoles, electric forces in molecular biology, DNA, photocopy machines and computer printers use electrostatics. Section 1: Static electricity, electric charge and its conservation. Some objects can be charged by rubbing. As you can see here on the left, part A, we have a piece of cloth which we are rubbing against a stick or a ruler here. And in part B, we can see as we make that ruler near some piece of papers, we will see the papers will be attached to the ruler because of the electric charge that we are inducing in the ruler. Charge comes in two types: positive charge and negative charge. Like charges repel and opposite charges attract. As you can see on the left, a ruler is hanging from a string and we are holding another ruler. Both are negatively charged in part A, and as we make the ruler closer and closer to the one which is hanging, we will see the one which is hanging starts rotating as it's being repelled by negatively charged ruler that we are holding in hand. In part B, we have a similar scenario, but we have both rulers positively charged, and as we get closer to the stick which is hanging, it starts rotating. In part C, one ruler contains negative charges and the other one that we have in our hand is positively charged. As we make them closer and closer, they start to attract to each other, and the one which is hanging gets closer and closer to the one that we are holding in hand. Electric charge is conserved. The arithmetic sum of the total charge cannot change in any interaction. Section 2: Electric charge in the atom. Here on the right, we will see a representation of the atom. As we can see, we have a nucleus at the center, represented with a red ball, which is confined in a small area and contains most of the mass of the atom, and is very massive compared to the rest of the atom, and it's positively charged. On the other hand, those elliptical lines with a minus sign, these are representation of the electric cloud, and the electrons are orbiting around the center as a nucleus positively charged, but the electron is negatively charged, and therefore they are in an equilibrium position that they are not either absorbed or they are not either repelled. So the electrons are very low density and they are negatively charged, and the cloud is very large compared to the small confinement of the positively charged nucleus at the center. Opposed to the previous example that we had distribution of the charges evenly, here we have polar molecule. In this condition, the atom is neutral, but the charges are not evenly distributed. As we can see here, the oxygen atom is negatively charged. There's two negative charges, but the hydrogen atoms, they are positively charged. The molecule of H2O, which is water molecule, is overall neutral and doesn't have any net charge. Section 3: Insulators and conductors. Conductors are defined as materials in which charge can flow freely. The most important example of conductors are metals. On the other hand, we have insulators in which we have no flow of charges. And most of other material than metals are insulators. Here in the bottom, we have two objects, one positively charged and the other one is neutral, chargeless. If we put a nail, a metal, the charges can transfer from the charged object to the neutral object in a way that the total distribution of charges stays equilibrium and both objects are equally charged. On the other hand, if we connect the two spheres of one electrically charged and the other one is neutral with a piece of wood, which is an insulator, no charges can flow and the wood stays neutral and the other object stays neutral. So we don't have any flow of charges. Section 4. Induced charge, the electroscope. Metal objects can be charged by conduction. So here in part A, we have a neutral metal rod, and in part B, we bring close a charged metal object, and as we have a contact between these two objects or rods, the charge can transfer from the charged object to the neutral object. We can consider a passage of electrons or negatively charged particles from one particle or object to the other one, or a transfer of the positively charged particles from the positively charged object to the other neutral object. Both have the same result. So we have a transfer of charges from a charged particle or object to the neutral object by contact. So it's by conduction. On the other hand, they can also be charged by induction, either while connected to the ground or they're not connected to the ground. Here again, we have an example of a neutral metal rod in part A. In the case of having this rod connected to the ground, and this is a symbol of being connected to the ground, we can see we have a wire here and we're connecting this rod to the ground, and this is a metal rod, right? So in part B, we have a negatively charged rod and we are getting it close to the metal rod. Since the metal rod is connected to the ground, electric charges can be extracted from the earth, and we will have a redistribution of charges on the metal because charges can freely flow inside the metal object or conductor. As we can see, we have a flow of electrons because they are repelled by the negatively charged rod, and they are flowing from the rod, the metal rod, to the earth. Therefore, we will have a lack of electrons or charges in the metal rod, and therefore the rod will be positively charged. If we disconnect the connection of the metal rod to the earth, as we can see it here, the metal rod will be charged positively. On the other hand, if we don't have any connection to the floor, to the ground, and therefore we don't have any flow of electrons from the rod to the earth, the distribution of the charges will be changed inside the metal because the charges are freely moving inside the metal, but overall the metal still stays neutral. What we will have, for example, here we're getting closer a rod which is positively charged. This is here, I'm talking about this part. As we get it closer to the metallic rod, we will see the charges are redistributed. Negatively charged particles go closer to the rod, which is getting closer. Note that we don't have any contact here, we just get closer, so there's a gap between these two rods, right? And the positive charges are getting repelled and they're getting farther and farther away to the other side of the metal rod. So what happens to non-conductors or insulators? These materials or non-conductors, they don't become charged either by conduction or by induction because we have neutral atoms inside the insulators, but they can be redistributed inside the non-conductor. So overall, it stays still neutral, they will experience a charge separation, as we can see down here. In the case of having a rod with a negative charge, the insulator will experience the opposite situation, and we have a separation of charges where positively charged sides of the atoms will stay on the left and the negatively charged side of the atom will be repelled to the right side. So we can apply the concept of repelling and attraction of charges and instrument device, which is called electroscope, and use this device to detect charges. Here we can see a cartoon showing the diagram of an electroscope. It's constructed by a metallic container, and this metallic container is isolated with an insulator here from the metallic part on top. Okay, and the metallic part on top is holding two leaves of gold. We have a glass window to see what happens to the leaves, and this device, as I said, is used to detect charges. Here in this slide we demonstrate how an electroscope works. The electroscope can be charged either by conduction or by induction. On the left, we are inducing charges by getting close, for example, with a positively charged rod. Well, the active side is a metallic structure. And as we can see, we will have induced negative charges on the top head of the electroscope, but we will have positively charged particles on the gold leaves. And because the gold leaves are positively charged, the two sides of the leaves will be repelled from each other and get separated. We can also charge the electroscope by conduction, by having a rod of positively charged in contact with the metallic head of the electroscope, as we can see here by contact, by conduction. And as we can see, positive charge can be transferred from the rod to the metal, the head of the electroscope. And as we can see, the whole electroscope is charged positively. So the positive charge can freely move inside the electroscope. And as we can see, again, the same story, the gold leaves will be repelled because they both are positively charged. So they don't want to be close to each other. They want to be as separated as possible from each other. Therefore, the charged electroscope can then be used to determine the sign of an unknown charge. Suppose that in part A here on the left, we have a negatively charged electroscope. We have added some negative charge to the electroscope by conduction, and we have negative charge on the gold leaves, and they are separated from each other. We already know that the electroscope is negatively charged, so we know it. Right? In part B, we are getting close a rod with an unknown charge. If it's a negatively charged rod close to the electroscope, the two leaves of gold down here will be separated even further, because all the negative charges will try to get farther and farther away from the negatively charged rod, which is getting closer to the electroscope. So we will figure out that by the isolation between the rods are getting farther, we will figure out that this object, which is getting closer to the electroscope, is negatively charged. In part C, we have the opposite scenario. We have a rod which is positively charged. And as we get closer to the electroscope, all the negative charges try to get closer to the head. They all freely flow toward the top part of the electroscope, and we have less and less charges down here in the gold leaf area. So we have less and less separation between the two gold leaves. And we will figure out that this object, which is getting close to the electroscope, is positively charged. And if, of course, nothing happens to the electroscope separation of the leaves and the gold leaves down there, we will figure out that this is not a charged object getting close to the electroscope. That's the way the electroscope figures out or is used to determine the sign of an unknown charge. Section 5. Coulomb's law. Coulomb's law describes the force between charges. Experiment shows that the electric force between two charges is proportional to the product of the charges and inversely proportional to the distance between them. Here we have two charges labeled as Q1 on the left and Q2 on the right, separated by distance r. Coulomb's law describes the magnitude of the force between the two charges, describing as F, the Coulomb force, the force between two charges, Q1, Q2, equals to K, which is a proportionality factor, or a constant, times Q1 times Q2, the magnitude of charge 1, the magnitude of charge 2, divided by r squared, the square of the distance between the two charges. The Coulomb's force is along the line connecting the charges and is attractive if the charges are opposite and repulsive if the charges are of the same kind. So we label the forces by a convection as F sub 1, 2, which is the force on charge 1 due to charge 2, and F21, the force on 2, the first number, due to the charge 1, which is the second number here. In part A, in the middle of this slide, we have charge 1 and charge 2, both positive. The force on charge 1 on the left, we label it as F12, which is a vector and is pointing to the left. Also, we have F21, which is opposite direction of F12 of the same magnitude, but is toward the right direction. For section B, we have two negative charges. F1, 2 on the left is leftward, and F21, the force on particle 2 or charge 2 from or due to charge 1, is toward the right. And in the third option is when we have two opposite charges. Charge 1 is positive, charge 2 is negative, but the forces are attractive. The two charges are attracted to each other by forces F12, force on charge 1 due to charge 2, and of F21, force on charge 2 due to charge 1. These two forces, F21 and F12, have the same magnitude, but they have opposite directions. The unit of charge is Coulomb, capital C, and the proportionality constant in Coulomb's law, K, is defined as 8.99 times 10 to the power 9 Newton times meter squared divided by Coulomb squared. As an example, charges produced by rubbing are typically around a microcoulomb. So 1 microcoulomb is 10 to the power minus 6 coulomb. So micro is an indication of 10 to the power minus 6. As another example, charge on the electron, or 1e, is equal to 1.602 times 10 to the power minus 19 coulomb. Electric charge is quantized in units of the electron charges. The proportionality constant K can also be written in terms of epsilon, 0, the permittivity of free space. The subscript 0 is representation of free space or vacuum. So we define K as 1 over 4 pi epsilon naught. And we can write the Coulomb force, F, as 1 over 4 pi epsilon naught times Q1 times Q2 divided by R squared. And epsilon naught can be defined as 1 over 4 pi K, and is equal to 8.85 times 10 to the power minus 12 Coulomb squared divided by Newton times meter squared. Now let's look at a couple of examples from the book. First, I'll go through problem number 4 in the textbook. What is the repulsive electrical force between two protons, which are 3.5 times 10 to the minus 15 meters apart in an atomic nucleus? So for solving this problem, we have to use the Coulomb's law to calculate the force and the magnitude of the force between these two protons. And these two protons are positively charged, so the force between them is repulsive, basically. So we write down the Coulomb's law by F equals to K times Q1 times Q2 divided by the separation distance between these two R squared. So K is 8.988 times 10 to the power 9 Newton meter squared divided by Coulomb squared. And the two charges Q1 and Q2 are equal, and their charge is equal to the charge of an electron, but positive. So in the numerator we have 1.602 times 10 to the power minus 19 Coulomb, and this is squared because we have two charges Q1 and Q2 equal. And in the denominator we have 3.5 times 10 to the power minus 15 meter. Everything is squared here. And if you do the mathematics to solve this, we will have F equals to 18.83 Newton, almost 19 Newton. Okay, now let's take a look at problem number 10 as another example. Compare the electric force holding the electron in orbit, and the radius of orbit is R, equal to 0.53 times 10 to the power minus 10 meter around the proton nucleus of the hydrogen atom, with the gravitational force between the same electron and the proton. Give the ratio of these two forces. So basically this problem is asking for the ratio between the electric and the gravitational forces. And let's write down the equation for the forces excuse me of electrical and gravitational forces. The electric force is the Coulomb's law, is K times Q1 times Q2 divided by R squared, and the gravitational force, F sub G, is equal to gravitational constant mass 1 times mass 2 divided by R squared, the separation between the two masses. Here, one mass is the mass of electron, and the other mass is the mass of the proton. So here we have the proton, here we have the electron orbiting around it. It's a hydrogen atom, and they are separated by distance r. So we have a proton with charge Q plus and mass m plus. We have electron, mass of electron, mass m minus, and charge of electron, charge minus. But their separations is equal to r for both cases of F sub G and F sub E. So if we take the ratio of electron force and gravitational force, the r squares in the denominator will cancel out. So in the numerator we will have K Q1 Q2 divided by R2. In the denominator we have G M1 M2 divided by R squared. So the distances will cancel out, and we will have the numerator K is equal to 8.988 times 10 to the power 9 Newton meter squared divided by Coulomb squared times the first charge is 1.602 times 10 to the power minus 19 coulomb, and the second charge is also the same but positively charged. So one charge is the charge of an electron, negative, and the other one is the charge of a proton, positive, but they have equal charges. So the magnitude is the same, so we'll have 1 electron squared, or 1.602 times 10 to the minus 19 coulomb squared. In the denominator, we have the gravitational force constant, 6.67 times 10 to the power minus 11 Newton times meter squared divided by kilogram squared times 9.11 10 to the power minus 31 kilogram, the mass of an electron, multiplied by 1.67 times 10 to the minus 27 kilogram, and this is the mass of a proton. If we simplify everything, you will end up with the ratio of electric force from Coulomb, or Coulomb force, divided by the gravitational force to be 2.27 times 10 to the power 39. That means that the electric force is almost 10 to the power 39 times stronger than the gravitational force for these two charged particles, an electron and a proton. Alright, now let's take a quick look at problem number 20 from the book as another example. Two charges, minus 2q and minus 3q, are at distance L apart. These two charges are free to move but do not, because there is a third fixed charge nearby. What must be the magnitude of the third charge and its placement in order for the first two charges to be in equilibrium? So we can imagine different scenarios, but it turns out that if we have charge minus 2q on here, charge minus 3q on the right, if we have, for example, a positive charge on the right or the left, these two will be attracted toward that, while these two are repelled from each other. Doesn't matter if the plus charge is on the left, on the right, on the top, or the bottom. We have the same story if we have a negative charge, either on the left, on the right, above, or below. But now let's consider the scenario where we have a charge between these two. So we have minus 2q on the left, minus 3q on the right, and we have a third charge. Let's consider if the charge is a negative charge in between these two. Separation between these two is L, as mentioned in the problem. If you have a negative charge, the charge in the left will be repelled from minus 3q, and also it will be repelled by the negative charge in the middle, so it will be extremely repelled. The right charge, minus 3q, also is repelled from the middle charge and also is repelled by the left charge. So there is not going to be any equilibrium. But we will have the final interesting scenario where we have minus 2q on here, minus 3q on here, and these two charges are free to move, but we have a third charge which we imagine to be a positive charge. What happens now? So this is a fixed charge, but these two charges are free to move. So we have, for the minus 2q charge, we have forces from the positive charge, attractive, forces from the minus 3q charge, repulsive. The same story for the minus 3q. We have repulsive from minus 2q and attraction force by the positive force. So in that scenario, we have forces on opposite directions can cancel out. So if we label them as charge 1, charge 2, charge 3, for minus 2q, we have force, repulsive force on 1 from charge 3, and also attractive force on charge 1 from charge 2. And if we consider the same situation for charge minus 3q, we have attraction force due to charge 2, so we have F force on 3 due to charge 2, and also repulsive force on 3 due to charge 1. And we should see in a equilibrium condition, these two conditions should satisfy. So from one condition, we can calculate the x, or the separation between charge 2 and charge 1. And the separation between charge 1 and 3 is L. Therefore, this separation can be calculated as L minus x. And also from another equation, so one equation will be used to calculate x, the other one will be used to calculate q, the amount of charge at place of charge 2. So we have two equations, two unknowns, we can calculate them. So let's erase my board to start doing the calculations. Okay, so we have a scenario where we have minus 2q, minus 3q, and we have a charge little q, and this is positive, and their separation between these two is L. We call the separation between these two x. Therefore, the separation between charge q plus q and minus 3q will be L minus x. And let's write down the equation between charge 1 and charge 2. Here's charge 3. So we have k minus 2q times q divided by x squared. So the separation between these two is x. And we're talking about the absolute value, the magnitude of the force. So we take the absolute value. And this should be equal to k, the force from particle 1, charge 1, and charge 3, minus 2q minus 3q divided by L squared. And again, we have the absolute value, magnitude of the forces. On the other hand, we have another equation. So this is basically F on 1 from 2 should be equal to F on 1 from 3 magnitudes. Another equation we have is F on 3 from 2 should be equal to F on 3 from 1. And let's write down this one as well. We have k times minus 3q times q divided by L minus x squared should be equal to k times minus 3q from minus 2q divided by L squared. Okay, so let's simplify these equations, and I'm just going to erase the extra. So for the top equation, we will see some parts will be canceled out. So we will have k cancels out, capital Q cancels out, 2 will be canceled out, the negative signs will be ignored because of the absolute value. So we will have q divided by x squared on the left hand side, we will have is equal to 3q divided by L squared. This is one equation. For the lower equation, again, we should have taken the absolute values. K's will be cancelled out. 3q's will cancel out. And it will be simplified as little q divided by L minus x squared equals to 2q divided by L squared, which is the second equation. So we have two equations, two unknowns. Let's solve it for these two equations. I'm just going to erase the board and write down what we have. Okay, now we have these two equations. Now let's solve them for little q and x. So from these two equations, we can see on the right hand side we have q, capital Q divided by L squared. So we can say here we have Q divided by 2L minus X squared is equal to capital Q divided by L squared. For this equation down here, we have little q divided by 3x squared is equal to capital Q divided by L squared. So the right hand side of these two equations are equal, so we can put the left hand sides equal to each other. So we have Q divided by 2L minus X squared equals to little q divided by 3x squared. Q's will cancel out and we can solve it for x. So we have 2L minus 2, and I just made a mistake here. This squared is actually here. So we have L minus X squared is equal to 3/2 X squared. And if we take this square root of both sides, we have L minus X is equal to the square root of 3/2 X. And we can solve it for X is equal to the square root of 2 divided by the square root of 3 plus the square root of 2 multiplied by L, and simplifies as X equals to 0.449 times L. So that is for X. And if you plug this X back to either of these two equations, equation 1 or equation 2, we will have Q is equal to X squared times 3Q divided by L squared. And instead of X, we will have 0.449 L. Let's square this one, multiplied by 3Q L squared, and the L squared will cancel out. What we will have is little q is equal to 0.61 capital Q. So the positive charge that you will have in the middle between these two negative charges is 0.61 capital Q, and the distance is 0.449 L with respect to charge minus 2Q, and we can say L minus X from charge minus 3Q. So this is the distance from charge minus 2Q. Section 6. The electric field. The electric field is defined as the force on a small charge divided by the magnitude of the charge. As you can see here, the electric field indicated by capital E, and this is also a vector because this is defined as the force divided by the charge, and the force is the vector, the electric field is also a vector. Here we have a charge capital Q, and we can imagine that we have an imaginary infinitesimal positive charge at the spot A, B, or C, and we can define the direction of the field by imagining what's the direction of the force applied to that imaginary infinitesimal small charge. An electric field surrounds every charge. Here we have a charge Q, and it's surrounded by electric field caused by this charge. Here there's no direction. If we have a positive charge or plus charge here, so the direction of the force or the field are away from this charge. So we will have fields out of this charged particle, because we can imagine at this point, at each point, we have an imaginary positive charge, and the field that this positive charge's field is away from the positive charge at the center. On the other hand, if we have a negative charge at the center, negative Q, the direction of the field will be inward. We will have field lines toward the charge, because if we have an imaginary positive charge, that charge would observe a force attracted toward the negative charge at the center. So the electric field for a point charge is equal to F divided by Q, and for the F we have K times Q divided by R squared divided by the little q, and the little q will cancel out. What we are left with is the electric constant K multiplied by the Q divided by R squared. This is for a single point charge of capital Q. Or in terms of epsilon, if we write K as 1 over 4 pi epsilon naught, we can write electric field for a single point charge as 1 over 4 pi epsilon naught multiplied by Q, the charge of the point charge, divided by R squared. So the force on a point charge in an electric field can be written as F equals to Q, the charge of that point charge, multiplied by the electric field, E, capital E. This is shown here in different scenarios of A, B, and C. On top we have scenario A. We have a point charge Q, and this is in the field of E. Therefore, the force of F is shown in section B. So we have a charge positive Q placed in the field of capital E, and the force that the particle is observing is F. On the other hand, for scenario C, if we have a charge minus Q placed in the field capital E, the force is opposite to the direction of the electric field. So to solve problems in electrostatics, electric forces, and electric fields, we first need to draw a diagram and show all charges with signs and electric fields and forces with directions. That's what I did in the previous examples in this course. And it should be your routine for solving problems in electric field and electric forces. Next, we calculate the forces using the Coulomb's law. And third, we add forces vectorially to get the results, because the final result will be a superposition of different forces at different directions. So we will have a vector sum, different components along x and y direction, and we have to consider those. And finally, we should check the logic of your answer if that makes sense. Section 7. Electric field calculations for continuous charge distributions. A continuous distribution of charge may be treated as a succession of infinitesimal point charges. The total field is then the integral of the infinitesimal fields due to each bit of charge. So here we consider dE as the infinitesimal field due to each bit of charge dQ. So dE due to dE. And we have to integral over all these infinitesimal fields to obtain the total field, capital E. Remember that the electric field is a vector, and you will need to separate the integral for each component along x and y, or along different axes in different geometries. Section 8. Field lines. The electric field can be represented by field lines. These lines start on a positive charge and end on a negative charge. The number of field lines starting on a positive charge is proportional to the magnitude of the charge. Same story for a negative charge, where field lines are ending on a negative charge. The electric field is stronger when the field lines are closer together, and the opposite can be said when the field is weaker and the lines are more spread apart. For an electric dipole, we have two equal charges opposite in sign. We have a positive charge on the left and we have a negative charge on the right, and the lines of the electric field are getting out of the positive charge toward the negative charge, and they are connected to each other. So we have an electric dipole here that the electric fields are extended from the positive charge toward the negative charge. The electric field between two closely spaced, oppositely charged parallel plates is constant. Here on the left we will see two parallel plates which have opposite charges, one plus Q and the other one minus Q, and we will see the electric field is parallel between these two plates, and it's a constant in the middle, but as we get closer to the edges the field starts to distorting. So in summary, field lines indicate the direction of the field, and the field is a tangent to the lines. The magnitude of the field is proportional to the density of the lines, and the field lines start on a positive charge and end on a negative charge. And the number of lines is proportional to the magnitude of the charge. Alright, at this point let's look at problem number 24 from the book as an example. Determine the magnitude and direction of the electric field 27.4 centimeter directly above an isolated 33.0 times 10 to the minus 6 coulomb charge. So here we use equation 21 4a to calculate the electric field due to a point charge, and that is E equals F divided by Q, and it's equal to 1 over 4 pi epsilon naught, or K, times Q divided by R squared. K, Q, R squared. And this is the magnitude of electric field. And let's write down the numbers and values. For K we have 8.988 times 10 to the 9 Newton per meter squared divided by Coulomb squared multiplied by 33.0 times 10 to the minus 6 Coulomb divided by 27.4 times 10 to the minus 2 to convert it to meter squared. If we do the calculations, we will have 3.95 times 10 to the power 6 Newton per Coulomb. And what is the direction? This is a positive charge. So we have a positive charge. The direction of the field at 27.4 centimeter above it would be upward. This is the E field. Because if you put an imaginary positive charge, the lines will be away from the point charge. Now let's take a look at problem number 34 from the book as another example. Determine the direction and magnitude of the electric field at the point P in the figure below, which is figure 2160. The charges are separated by the distance 2a, and point P is a distance x from the midpoint between the two charges. Express your answer in terms of Q, X, A, and K. So at point P, we have to consider the field at this point. Let's consider a coordinate system in which anything to the right is positive. So anything toward right is considered positive. So if we consider a field at this point, one field is due to charge plus Q on the left, and that would be positive to the right, and one field would be due to charge minus Q on the right, and that would be leftward. So we have to add them together and see what's the net field, and therefore what's the direction of the net field at point P. So the field due to charge positive, again, is toward the right, so it's going to be positive. So we write down E is equal to K, Q, and this is going to be positive, divided by, and the separation is X plus A. So here is X, here is A, x is the midpoint between the two charges. So we have x plus a squared. And the field due to a negative charge is toward the left. So it's going to be negative kq divided by x minus a squared. So we can factor out k times q, 1 over x plus a squared minus 1 over x minus a squared. If we simplify things, we will have minus 4kq xa divided by x squared minus a squared, everything squared. So this is going to be a field, the net field, and because this is negative, it means that the net field would be toward left. And that is reasonable because the charge negative q is closer to point P. And that means that it's in a stronger field compared to the point charge plus q on the left. And the dominant field would be toward the left on point P. Another example, let's look at problem number 44 from the book. Estimate the electric field at a point 2.4 centimeter perpendicular to the midpoint of a uniformly charged 2.00 meter long thin wire carrying a total charge of 7.45 microcoulomb. Because the distance between the wire is much smaller than the length of the wire, then we can approximate the electric field by wire, which is derived from example 21.12. So from that equation and from that example, the electric field is 1 over 2 pi epsilon naught lambda divided by x. And lambda is the charge density, charge per meter, and x is the distance from the charge line. So let's plug in the numbers. So we have 1 over, we can say 4 pi epsilon naught 2 lambda divided by x, and by this we're constructing the electric constant, which we can substitute it as 8.988 times 10 to the power 9 Newton per meter squared, Coulomb squared, multiplied by 2, and lambda is 7.45 times 10 to the power minus 6 Coulomb, divided by the length of the wire is 2 meter. Okay, therefore we will have the density, which is charge per length of the wire, divided by x, which is 2.40 times 10 to the power minus 2 meter. If we simplify everything, electric field, the magnitude of electric field would be 2.79 times 10 to the power 6 Newton per Coulomb away from the wire, because the wire is carrying a positive charge, and at point 2.4 centimeter away from it, the field will be away from the wire. Section 9. Electric fields and conductors. The static electric field inside a conductor is 0. If it were not, the charge would move. The net charge on a conductor resides on its outer surface. So if you put a positive charge, as it's demonstrated here, inside a conductor, it will induce charges on the surface of the conductor in a way that the negative charge will be populated inside this conductor, and they will be separated from the positive charge because the whole sphere is neutral. There is not going to be any charges on the conductor. But we have a positive charge inside the conductor. Therefore, it will induce the charges outside of the conductor. Outside of the conductor will be positively charged. If we look at the electric field inside a conductor, there is no electric field, and the net charge inside the sphere, if we say what's the charge inside this sphere, there's a negative charge populated inside the sphere, so the net charge is 0, and all the charges are induced on the outer surface of the sphere here. So the electric field is perpendicular to the surface of a conductor, and if it were not, charges would move. So here we have a good conductor here, and the electric field is perpendicular to the surface of that conductor. So we have at each point component of the field parallel and perpendicular to the surface, E parallel and E perpendicular. And we can say if E parallel is not 0, it would force the charges on the conductor to move inside the conductor, and we don't see that, so we don't have any parallel component of the field, and all the fields are perpendicular on the surface of the conductor. Section 10. Motion of a charged particle in an electric field. The force on an object of charge Q in an electric field E is given by F equals to charge times field, Q times E. Therefore, if we know the mass and charge of a particle, we can describe its subsequent motion in an electric field. Okay, at this point I'll look at problem 54 from the book as an example. An electron has an initial velocity v0 equals to 8.0 times 10 to the power 4 meter per second j hat, which means that it's along y direction. It enters a region where the field E is equal to 2 I hat plus 7 j hat times 10 to the power 4 Newton per Coulomb. A. Determine the vector acceleration of the electron, and B. At what angle theta the electron is moving relative to its initial direction, which was along y direction at time 1 nanosecond. So we can draw what the problem looks like. So this is x and y direction, and we say the velocity of the electron is along positive y, so this is v0, and it enters a region where the field has components along 2 components along x and 7 components along y. So this is 2 components along x, this is 1, 2, 3, 4, 7. So this is the electric field. So we have an electric field at this direction, so this is electric field E. And it asks what is the angle theta that the particle would end up at 1 nanosecond after it enters. So this is at time equals 0, and what happens at t equals 1 nanosecond. So we know that this electron, which has a negative charge, is going to be repelled, deviating from the initial motion it was going upward along y direction. So we should start with calculating the force, and then from the force we can calculate the acceleration. This is going to be an accelerated kinetic problem, and with knowing the acceleration from the force, we can calculate the velocity at time t, 1 nanosecond. And for the direction, we can calculate the direction of the v velocity at time 1 nanosecond and take the tangent of that direction and calculate the theta that is forming with respect to initial direction y. Alright, so for part A, we have to first calculate the force, then we can obtain the acceleration. So force is equal to charge Q times electric field at that point, And also we know that the force is equal to mass times acceleration. From here we say acceleration is equal to charge q times electric field divided by mass m. And charge q is the charge of an electron. So q is equal to minus e, right? Let's plug in the numbers and calculate the acceleration. So it's going to be minus 1.60 times 10 to the power minus 19 coulomb divided by the mass of an electron, which is 9.11 times 10 to the power minus 31 kilogram. And we should multiply this by the electric field, which is 2.0 I hat plus 7.0 j hat times 10 to the power 4 Newton per coulomb. If we do the calculations, we will have acceleration A is a vector, of course, and it's going to be minus 3.513 times 10 to the power 15 along I direction minus 1.229 times 10 to the power 16 along y direction or j direction, and the unit is going to be meter per second squared. Okay, so this is the vector acceleration of the electron. It's for part A. For part B, it asks for the angle of theta, that is, the particle is going to be moving at after 1 nanosecond. So we should solve this from the kinetic equations. Velocity v is going to be initial velocity plus acceleration times t. The initial velocity is 8 times 10 to the power 4 meter per second j hat plus minus 3.513 times 10 to the power 15 I hat minus 1.229 10 to the power 16 j hat, and this is meter per second squared. And we should multiply it by time, which is 1 times 10 to the power minus 9 second. This is the time. If we do the calculations, velocity vector will be minus 3.513 times 10 to the power 6 along I hat minus 1.221 times 10 to the power 7 along j hat. The unit is meter per second. So this is the acceleration vector. This is the velocity vector after 1 nanosecond. And for part B, we have to calculate the theta. So what's the angle which is forming? So we say this is x direction, this is y direction. The initial directional velocity was along y direction. Now we have component along x and y direction toward the negative x and negative y direction. So what we should do is take the tangent and tangent inverse of vy by vx. And if we take the ratio between this component to this component, we will have 1.221, tangent inverse of 1.221 times 10 to the power 7 divided by 3.513 times 10 to the power 6. So this gives us 254, or 106 degrees minus 106 degrees relative to x-axis. Relative to x-axis. What we need is actually the theta, the axis that the velocity is forming with respect to the initial velocity, v0. And in order to obtain theta, we should subtract 90 degrees from that. So we say 254 minus 90 degrees, and it gives us 164 degrees with respect to axis y, which is the initial direction. Section 11. Electric dipoles. An electric dipole consists of two charges Q equal in magnitude and opposite in sign, separated by a distance L. The dipole moment P, which is a vector, is equal to charge times distance or separation between these two charges is equal to Q times L, points from the negative to the positive charge. An electric dipole in a uniform electric field will experience no net force, but it will, in general, experience a torque. A torque tau is equal to force multiplied by r, the distance from the point that the force is being applied. And we know force is written as Q times electric field. And we know from the previous slide, we defined Q times L or R as the dipole moment. So Q times R is defined as P, dipole moment. So we will have tau, torque, P, which is a dipole moment, multiplied by the electric field E. So we'll have P multiplied by E. And we have a vector product, so we have Q times E, L half, which is the half of the dipole moment separation, multiplied by the sine theta. So we have half of the torque is applied to the upper charge, and half of the torque is applied to the lower charge. So the net torque is equal to P E sine theta, or the P multiplied by the E. Sine theta is the axis, is the angle between the dipole moment and the electric field, the constant electric field. The electric field created by a dipole is the sum of the fields created by the two charges far from the dipole. The field shows a 1 over r cubed dependence. So here we have charge minus Q, and also we have a charge plus Q separated by the distance L from each other. And at the midpoint O, and vertically up at a distance R, we have a point P. And at this point, we have electric field from the positive charge showing upward, and we show it as E plus. And we have electric field due to a negative charge, E minus, and the overall field will be in superposition between these two, and we define it as E. And this electric field has a dependence to the distance r from the midpoint of the dipole moment of these two charges down here as 1 over r cubed. So here I should emphasize that this r is not the distance from P to charges minus Q and plus Q. Instead, r is the distance from point P to the midpoint of the dipole moment down here, and the distance r is written as r squared plus L squared divided by 4 to the power 3 half. So if we look at the point on perpendicular bisector of dipole, the electric field is defined as 1 over 4 pi epsilon naught P, which is the dipole moment of the charges down here, divided by r squared plus L squared over 4 to the power 3 half. And if the distance from the point P is much larger than the dipole moment separation between the charges L, we can neglect L with respect to R, and we can have electric field equals to 1 over 4 pi epsilon naught P divided by R cubed. Okay, I'll look at problem number 60 from the book as an example. The HCl molecule has a dipole moment of about 3.4 times 10 to the power minus 30 coulomb meter. The two atoms are separated by about 1 times 10 to the power minus 10 meter. A asks, what is the net charge on each atom? And B is asking, is this equal to an integral multiple of E? If not, explain. C asks, what maximum torque would this dipole experience in a 2.5 times 10 to the power 4 Newton per Coulomb electric field? And D is asking about how much energy would be needed to rotate one molecule 45 degrees from its equilibrium position of lowest potential energy. So to solve part A, we should refer to the definition of the dipole moment, which is the effective charge of each atom times the separation distance between these two charges. So for part A, we have dipole moment equals to Q times L. So we can solve this for charge Q as dipole moment divided by the separation. We have 3.4 times 10 to the power minus 30 Coulomb times meter divided by their separation, which is 1.0 times 10 to the power minus 10 meter, and that simplifies as 3.4 times 10 to the power minus 20 Coulomb. For part B is asking if this charge is a multiplication of electric charge E. So we divide Q by E, which is 3.4 times 10 to the power minus 20 Coulomb by 1.6 times 10 to the power minus 19 Coulomb, and it gives us 0.21, which is not an integer multiplication of the electric charge. This is an indication that the atoms of hydrogen and are not ionized, and they haven't fully gained or lost any electrons, but they are rather sharing electrons, parts of the electron fields. And the electron spends more of the time near some atoms of chloride atoms rather than hydrogen atoms. Therefore, that is causing a net dipole moment of the molecule. And the electrons are not symmetrically distributed between the two atoms. For part C is asking for the torque that the dipole moment is experiencing. So we have the electric field, and we should calculate the torque. And from equation 21.9, so 21.9a, the torque tau is equal to P, the dipole moment, times electric field times the sine theta. And the maximum of the torque is when the sine theta equals to its maximum, which is 1 at 90 degrees. So we have the dipole moment of 3.4 times 10 to the power minus 30 Coulomb times meter multiplied by the electric field, which is 2.5 times 10 to the power 4 Newton per Coulomb, and that gives us 8.5 times 10 to the power minus 26 Newton times meter. And this is the maximum torque that the dipole moment can experience. For part D, we say we use the energy needed from an external force is the change in potential energy. So we use equation 2110 from the book, which says the work done to change the internal energy is equal to minus PE cosine theta final minus PE cosine theta initial. Okay, and if we factor out PE, we will have cosine theta initial minus cosine theta final. Okay, so it's asking about rotating the dipole moment of one molecule 45 degrees from its initial equilibrium position of lower energy. So we say this is equal to 3.4 times 10 to the power minus 30 coulomb times meter multiplied by electric field of 2.5 10 to the power 4 Newton per coulomb multiplied by the initial theta is where the molecule is at equilibrium, where we have theta equals 0. When the theta is equal to 0, we have cosine theta equal 1, and the final theta is when we have theta equals 45 degrees, okay? So we plug in this number. So for theta of 0, we have cosine theta is equal to 1, and for cosine theta of 45, we should do the calculations, and we end up in 2.5 times 10 to the power minus 26 joule. And this gives us the energy needed to rotate this molecule by 45 degrees from its equilibrium position. Summary of chapter 21. Two kinds of electric charge, positive and negative, exist. Charge is conserved, and the charge of an electron is 1.602 times 10 to the power minus 19 coulomb. The coulomb is the unit of charge. Conductors have electrons free to move, while insulators are non-conductors and electrons are not allowed to move. Charge of materials is quantized in units of the charge of an electron, E. Objects can be charged by conduction or induction if they are in touch or if they are inducing charge to each other. The Coulomb's law defines the force between two charged particles and defines the magnitude and the force between those charges, and is given as K multiplied by Q1 Q2 divided by R squared, and K is a constant defined as 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space, and is defined as 8.85 times 10 to the power minus 12 coulomb squared divided by Newton times meter squared. Electric field is force per unit charge. It is defined as force divided by charge. The electric field of a point charge is defined as force divided by charge, F divided by Q, and it can be simplified as K times Q divided by R squared. Electric field can be represented by electric field lines. Static electric field inside conductor is 0. Therefore, surface field is perpendicular to its surface.